Welcome, everyone. We are back discussing Grossberg's book, Conscious Mind, Resonant Brain, and we're on deep in the middle of chapter 12, which has a whole lot of stuff that is sort of related, but at the same time could have been split up maybe more because there's a lot in there. So today we'll look at, so we talked about a couple of the motor control models, and from there we talked about sequencing, competitive queuing. And here we're kind of moving back to Steve's wheelhouse, which is art-like models based on adaptive resonance theory, and basically how to do art-like processing for the auditory stream, which is very rapidly changing in time, and some particular quirks of that type of modeling. So yeah, we were last week talking about the DIVA model, that's Frank Gunther's model, which is basically an oral to oral hearing to speech articulator version of the inverse kinematics problem. We also talked about competitive queuing, which is a really elegant idea, and of all the Grossberg style models, this is the one that's most sort of out there and popular, and has displaced the older shift register based ideas about sequencing. There's a lot of neural evidence for this now that started accumulating since 2002 or so. So from the production of movements, planning and production of movements, to the sequencing, we can kind of zoom in on something that, so in most of these Steve models, there'll be some box that's kind of assumed to be a certain way, and then he gets a grad student or postdoc to kind of go in and say, well, what can we say about that, and what needs to be elaborated in that particular box? And that becomes someone's thesis or postdoc project. So in the case of hearing, there are particular things that are really interesting that people who study audition will often tell you about. But it's often the case that with these different psychophysics fields, that there is kind of tunnel vision, where the vision people know all kinds of quirky things about vision and haven't heard much about what's going on in audition. But this one I think a lot of people have heard, which is that when you play a complex note, like something other than a sinusoid, it has harmonic overtones as a result of the way that a string will vibrate, that kind of thing. And you can, and so when you play something, either a pure tone or one of these complex tones, you'll hear a particular pitch. So people often think the pitch is the same as frequency, but not quite. And this is a great way of illustrating why, because you can remove the fundamental frequency artificially from a complex sound, and the pitch sounds more or less the same. So that's called the missing fundamental issue problem. So yes, this is a useful website that has a lot of demos. So if you want to hear what it sounds like, each of these demos, you can check it out. I find these pure tones a little bit irritating to listen to, but yeah, you can check them out. But they sound pretty much the same. You can definitely tell that the timbre changes when you remove the fundamental frequency, but it doesn't sound like the pitch is shifted by an octave or more than an octave. So another really interesting set of illusions arises because of shepherd tones, where you use sinusoids that are separated by an octave, and those are called shepherd tones. And if you play a scale of shepherd tones, you can create an illusion of constantly upward movement. And one of the most famous examples is from the Pink Floyd track Echoes. So right at the end, just as the song is ending, they play a shepherd tone, I guess, with some sort of sequencer, and it has this constantly ascending kind of sound. It's quite interesting to hear. And some people have described it as the auditory equivalent of the barber pole illusion, which Steve has a model of this. We didn't actually get into it when we went through the vision stuff, but he definitely thought about this sort of thing. And so another really cool thing that I didn't really know about until I read about it in Steve's book was the tritone paradox. And he brought it up in the context of reviewing a whole lot of data about hearing, and I didn't quite understand what the effect was, but the actual paper that talks about it is very short and very well written and clear. It's like 5 pages or something, and So they use uses shepherd tones again, and so there's an ambiguity that you can create. So with shepherd tones, depending on if you play a note that's above or below, you can get a continuously ascending or continuously descending sound. So you might think, well, naturally, well, what happens if I play the tritone, which is exactly on the opposite side in the octave circle? There's some ambiguity there. And this is, in fact, what they find. So that when they played pairs of notes that were shepherd tones that were a tritone apart, users differed, like listeners differed in terms of whether they thought of it as a note going up or down. It's quite amazing. So this is the way they constructed the stimuli. So the dotted lines were, yeah, so those were pairs of notes. And basically, these are individual subjects that for different pairs. And so they differed quite a bit about where they would decide that a particular tritone was going up versus going down. So it looks like this. So it appeared from these results that the orientation of the pitch class circle, like you might, if you don't have any music theory at all this will sound very like, obscure, but it's not actually that difficult, but it takes a little while to explain all of this. But but basically octave similarity is the idea that when you double a frequency, it sounds like the same note. So you can divide up that range into a circle, but it's sort of like a spiral staircase. So things that are directly above on the spiral staircase have the same note quality. So C versus a C an octave up. So that's the circle we're talking about. So that the orientation of the pitch class, so it's like if for the higher and lower, you still need to kind of pick an orientation. So it's like a circle, but where do you pick as up versus down? That apparently is sort of haphazard between different listeners, which is really interesting. This is an example. So one listener could transcribe a particular set as one way, and the other is completely the opposite. So down versus up can be ambiguous in this case. So the finding that listeners are able to refer to the absolute positions of tones along pitch class circles in making judgments of height shows that the possession of absolute pitch is, in a sense, considerably more common than has been assumed. That's also quite interesting, that there's a kind of absolute reference point people are using, which differs from person to person. So this, Steve, in his model, they kind of address a version of this. So they talk about how this might arise. And this is the model that does this. So it's using principles that we've seen before, competitive dynamics and top-down and bottom-up interaction, specifically to process sound. So it's the spectral pitch network, it should be. So it uses something called a harmonic sleeve, which is an interesting kind of thing that you need specifically for sound, which there's nothing equivalent to that really in vision, which we'll get to in just a sec. But it's in order to produce basically categorizations of the pitch class, like what is the pitch in these kind of complicated situations where you have rich tones. And this is the structure of the model. It's actually quite a detailed and quantitative paper which is kind of closer to almost digital signal processing than neural networks. So if you're interested in this sort of thing, they've modeled a lot of data, which I won't be able to really get into much. But basically, like all these models, you start at the bottom with some sort of input and work your way up. You have a gamma tone filter bank, which is a particular sort of way of modeling the basilar membrane, more or less. It's a little bit like like a Fourier transform to some extent in the way it works. You're basically transforming to a frequency space, and the height, these overlapping filters kind of mark where the energy is in that particular frequency band. Then you have some more sort of pre-processing, basically, and then you have what we're very familiar with: on center, off surround, competition, and rectification. Here, rectification means things that are below a certain value of are treated as 0. And then there's this harmonic summation, which we'll get into why this is needed. But just a brief review of the auditory system. The cochlea, you guys probably know what it looks like. It's the bones of the eardrum cause vibrations on the round window, right? Or is it both windows? I forget. And if you sort of stretch out the cochlea, you get this structure where the high frequencies cause vibrations near the one end, and the low frequencies cause vibrations all the way near the other end, the apex of the cochlea. And they move little hair cells around, and the hair cells get electrically stimulated, and then you end up with a place code that goes to the cochlear nucleus, and from there to auditory cortex. So in auditory cortex, you see what's called a tonotopic map. So it's arranged roughly in order of frequency, low to high. So the harmonic sleeve is related to the fact that, so tonotopic maps like the one we just saw, spatialize sound. So sound is this time-varying, one-dimensional quantity, but you can turn it into a spatial code by doing something analogous to a Fourier transform. And when Steve uses spatial in this context, it doesn't mean like 3D space or Euclidean space. He means something that's where most of the information is in the time domain has been laid out. In this case, in a band of neurons. So that's what spatialization means. But harmonics belonging to a complex sound, which are in some sense close together, are not adjacent. So that is where this harmonic sieve idea, which Steve himself didn't come up with, that's been around. That's where that comes in. So it's a kind of template matching. So you have to literally think that there are holes in a kind of like pattern that you're sort of moving around a frequency domain pattern. And if you fit in with the fundamental and the harmonics, you're like, okay, yes, it's that particular pitch class. At one point, people thought of it as sort of a binary thing where it's like, does it have this frequency or not? But there's, as you might expect, more subtle than that. You can mistune some of the higher harmonics, and there's a quantitative effects of how much you mistune to produce a change in the subjective pitch quality. And interestingly, there are thresholds here, so you can bend these, you can pitch shift the harmonics, leaving the fundamental frequency alone, and for a while you'll get these upward shifts in pitch, then it'll stop and then go backwards, and then the listener stops caring about those harmonics. Inharmonics, they call them. After a while, they don't really belong in that sound, basically. So this and a whole lot of other quantitative data has been reviewed in this paper to make basically a sort of Grossberg style harmonic pitch in using adaptive resonance theory style mechanisms. So basically, you want to group harmonics that are part of the same thing, 100 hertz, 200, 300, 400, and then shifted, another group of harmonics need to be together. So that's why cells that are adjacent to each other. So if you were to make a normal competitive network out of a tonotopic map, and you had an on-center, off-surround kind of connectivity, then 100 hertz would inhibit not only adjacent frequencies, but also its own harmonics. And you don't want to do that. So you, in their case, you kind of bake this in, that harmonics of a particular frequency all feed in to a particular higher level node. Yes. So this they kind of model a whole lot of phenomena related to low level auditory perception and pitch perception. But they have the eyes on things going further. So this relates to the cocktail party effect, which I'm guessing a lot of you have heard about, which is that when you're attending to one person, when there's lots of sounds going on, lots of people speaking, so there's lots of overlapping frequency sounds that are different information streams, we're able eventually to latch onto one of them and parse it, even in a relatively loud party. Not everyone can do this equally, so there are people who find it much more difficult. So Steve, when in the Artstream model, which we're about to talk about, he cites this book. and just from the way that Steve brought up this book, I could tell that there must be a lot in here, because normally Steve doesn't, direct people to one book that way. He's like, if you need to know more about this topic, please read this book. That was the tone of it. And I just quickly looked at it today just to get a flavor for it. And I was rewarded because there was good stuff to be found here. It was fortunate that I had never been trained in auditory perception and had only the most primitive idea of the structure of sound. I was free to pursue the phenomena as they unfolded. The fact that I was willing to strike off in a direction I knew nothing about can be blamed on one of my teachers in graduate school at Yale, Neil Miller. Miller advocated this strategy. If a phenomenon is strong enough to get in the way of something that you are trying to study, then perhaps it is worth studying in itself. He called it the making a silk purse out of the sow's ear. So auditory stream segregation got in the way of a study I was trying to do on auditory learning. I decided to follow Miller's advice. I thought it was a detour, but the detour has occupied about 20 years. That's awesome. So yeah, so what are streams? So he kind of coined this term auditory scene analysis, and what is it? So he thought that he was trying to explain why he thought there would have been a lot of understanding of audition, but then as it turned out, not much in the early 60s. So he predicted, I think accurately, that with the advent of computer generated sound, there would be a lot more progress, because basically controlling in a very careful way visual stimuli was already fairly easy by the middle of the 20th century, but auditory signals took a little while. But then he raises another possibility about the slighting of audition in the textbook. Perhaps audition really is a much simpler sense than vision. But then he immediately says this is a notion to be rejected. We can show that such complex phenomena as constancies like exist in hearing too. One example is timbre constancy. This is a good one. A friend's voice has the same perceived timbre in a quiet room as at a cocktail party. Yet at the party, the set of frequency components arising from that voice is mixed at the listener's ear with frequency components from other sources. The total spectrum of energy that reaches the ear may be quite different in different environments. To recognize the unique timbre of the voice, we have to isolate the frequency components that are responsible for it from others that are present at the same time. So it's a very neat analogy with the kind of thing that Grossberg likes to draw attention to in vision, all that Gestalt stuff about factoring out the illuminant. So there is clearly an auditory analog, and there's nothing trivial about it. So here he clarifies what he means by auditory scene analysis. I put this here because it's a nice kind of argument for representation. Perception is the process of using the information provided by our senses to form mental representations. And we are implying a two-part system. One part forms the representations and another uses them to do things such as calculate appropriate plans and actions. The job of perception then is to take the sensory input and to drive a useful representation. And in the case of any kind of sense, unless we put the right combination of sensory evidence together, we will not be able to recognize what's going on. So there's pieces of things that are coming at us that are mixed, and we have to separate them. And here's an example of this. The first set of letters makes very little sense, but if you split them into two streams, there are two sentences you can see. It took me a moment to actually see what was written there. A cat sits, I sit too. So what is a stream? We've been using this word metaphorically and colloquially, and people kind of get it when you use it, but he kind of explains why he chose to use this term, Bregman. An auditory stream is our perceptual grouping of the parts of the neural spectrogram that go together. To see the reasons for bringing in this concept, it is necessary to consider the relations between the physical world and our mental representations of it. As we saw before, the goal of scene analysis is the recovery of separate descriptions of each separate thing in the environment. What are these things? In vision, we are focusing on objects. Light is reflected off objects, bounces back and forth, blah, blah. So we know what objects are in vision, but so what are the equivalents in hearing? In a sense, it's the events or the things that produce the sound, but that's not such a simple, it's not necessarily a punctate thing. A physical happening can incorporate more than one sound, just as a visual object can have more than one region. A series of footsteps, for instance, can form a single experienced event, despite the fact that each footstep is a separate sound. I like that example a lot. Soprano singing with the piano accompaniment is also heard as a coherent happening, despite being composed of distinct sounds. So our mental representations of acoustic events can be multifold in a way that the mere word sound does not suggest. And also he wants to distinguish it from sound itself, because the sound refers indifferently to the physical sound in the world and to our mental experience of it. It is useful to reserve the word stream for a perceptual representation, and the phrase acoustic event or the word sound for the physical cause. Nice and clear. So Artstream is an adaptive resonance theory based a way of doing auditory stream analysis, which is I'm receiving all this auditory energy. It's all mixed in. It's almost one-dimensional, sort of two-dimensional, because of the two ears having slightly different, receiving different signals. So one of the examples that they talk about in this paper is the auditory continuity illusion. So if you have a sound playing, and this line represents the fundamental frequency of it, and then there's broadband noise, and then that sound again. If you don't have the sound after that, you hear the sound ending. But if you have the sound on the other side of the noise, it's as if the percept usually is of the sound being continuous through the noise. Seems quite obvious to in some sense, but it's something to be explained, because it seems like the sound seems to end when at the moment of the noise without that subsequent continuation. So this is one of the simpler examples of what Steve likes to describe as backwards effects in time, although they're not backwards. Does this not seem to require that the brain can operate backwards in time to alter its decision as to whether or not to continue or pass on through the noise based on future events? So this is the way he frames it, and it's interesting because it gets to some sort of tricky philosophical stuff, which if we have time we'll get to today. In this paper, they look at a whole lot of different kind of examples of where streams get separated, and you need to kind of explain how this happens. So in all of these figures, there's schematics showing the fundamental frequency of a sound that's in this case composed of a bunch of different pieces, and down here is the two different streams that one tends to hear. So rather than hearing like one big zigzagging sound, you hear sort of small zigzag in the lower frequencies, and then two sort of discrete little zags on top. And this you hear when there isn't this noise, and even when there's noise at those sort of nodes where the splitting happens. And you can kind of bias the system towards different kinds of, so in some cases, when you have streams that cross, you can get a sound like going down and then bouncing and going back up, rather than one stream that keeps going down and another that keeps going up. And you can bias this depending on how much you mix the presence of multiple frequencies. The order from greatest to least is the rich bouncing, all pure, and all rich. So these are the kinds of things that they want to explain, which is how do we create these separate streams that seem to have their own frequency? You can see that these are like toy kind of approaches to separating voices, the more complicated thing that we're interested in. That we're presented with even meaningless stimuli that we tend to split perceptually. So basically what Artstream does is multiplex sound features. You take sound features that you've processed, such as in the Spinet model, you split them up into different pitch classes. So things like pitch class and maybe other features that you can learn are not the same as frequency. So you start with those things and you split those into multiple streams. You make copies of them. So basically this is, I guess you could say, the kind of the brute force approach, which is to say that you have slots, 4 streams that you populate. And then the sort of classic competitive cooperative dynamics happen among and across these separate slots. This is just another version of it. So yeah, the frequency slots. So not only the sort of pitch classes, but even the spectrum is split up, because Steve will have a resonance between a categorical node like the pitch class and the actual spectrum itself. So there'll be top-down excitatory feedback. So yes, so basically each stream contains both high-level features, which are still perceptual, but they're not just pure frequency, as well as the spectral map. And so Artstream addresses this issue, which I briefly mentioned, that harmonicity and frequency proximity interact. And so the splitting of streams, there's two things that happen. There's harmonic content that we often relate to the same sound, but there's also, as you could see from some of those tasks, that frequencies that were closer to each other tended to be grouped together when the fundamental frequency was moving. So this is a schematic showing like with two sounds, how they get populated in two streams, where you start with, I think, where does it start? Yeah, up here. So you have input, and then through pre-processing some kind of energy measure of where again spatializing in tonotopy space, and that's copied into the two streams. And we're looking at 3 different time points during this competitive process. So they introduce a sort of bias, so that stream 1 is biased toward one set of frequencies or pitches, and stream 2 is biased to another, and you get top-down feedback. So at the end of a kind of competitive cycle, the pitch, which is the category in this case, causes amplification of one of the two spectral sounds in each stream. So now each stream has a consistent separate pitch class and feature set, and that's basically what the model does is, and it involves competition across streams. So they're like fighting for, no, that's my frequency, that sort of thing. That's basically the idea. The different streams are competing to take ownership of certain frequencies. Yeah, so everyone's going to run their own separate stream. Yeah. If they have
Yohan, go back. Huh? Yohan, go back to the previous slide. There is another reason why he's doing this multiplexing.
Okay.
It is not simply the case that he's doing it for the sake of multiplexing it. Unlike vision, most of the features that you want to extract in the auditory stream are way up in the cortex itself, in the sense that you don't have the luxury that you have with say vision, where V1 does the V1 acts as the spectrum analyzer in a way in visual cortex, right? So you have already extracted certain qualities of the signal in the cochlea and the cochlear nucleus itself.
Right.
So what the sound features, what features you get to when you get to the sort of like multiplexed art version is that it's sort of like Steve saying that if given that the auditory cortex is itself sort of organized like a tonotopic map, it is actually acting along those different multiplexed locations in the tonotopic map itself. So that's kind of the reason why it is like slotted this way.
So what you're saying is that auditory cortex itself is already a multiplex representation.
Yes, exactly.
Because there's more than one, I mean, like there's quite a few neurons that represent the same pitch.
The same pitch, exactly. Yes.
Yeah, the neural real estate, there's plenty of it. Might as well use it in these ways. Right, that's a good point. Right, so you split these things up, and then they each kind of take over. There's some subtleties when there's overlapping kind of frequencies in both streams, but I think it sorts that out.
So is this happening at the cortex, or is it starting in the brainstem and working its way up as it goes up?
The general assumption is this isn't a fully corticalized model, but the general assumption is that a lot of this is happening in cortex.
Okay.
When we get to solve the model, there's some attribution of cortical layers, but Steve hasn't necessarily come up with like fully incorporating subcortical areas into sort of high-level processes. So he does kind of lean in that sort of cortical chauvinism direction, although he has done quite a bit of basal ganglia modeling and some cerebellar modeling.
Okay.
So he's looked at that, but maybe if people are nowadays kind of more sort of radical in saying that there are cognitive processes that the basal ganglia does, then Steve hasn't necessarily put that into his model. But
there's just so much that happens right there where the auditory nerve is coming in. And all that. I mean, I've never been able to get my head around audition. I can get the mechanics of it all down, but the processing part just.
Saurabh can correct me. Answering Mike's question, I would say this, at least the top part of the Artstream model is firmly in the cortex for Steve, for a very precise reason that he is no longer interested in pure signal processing aspects of the stream. He is interested in sort of the equivalent feature extraction and feature categorization aspects of auditory data. So he would sort of telescope all the questions about signal processing and everything to the basilar membrane, the inferior colliculus, and all that stuff. So he all this processing, I would say, of saying that there is a stream 1 with one pitch and stream 2 with another pitch, and it's actually in competition, and they're actually like the spectral aspects are in some of the cortical area, but the pitch layer would definitely be in or some auditory cortical area for him.
Yeah, definitely agree. I think the interesting thing about Steve is also that you should imagine a lot of these principles would apply independent of what those sort of subcortical or initial like pre-processing areas would look like. So the similar question would apply if the basilar membrane wasn't doing like effectively in a Fourier transform, and the input looked somewhat different, or if you didn't have, you know, a retina that was, you know, necessarily in exactly the way or organized in the way that a human retina is organized, like how does the cortex nevertheless process those inputs and give rise to certain phenomena in the same way? And I think that's basically one of the things that makes the same principles apply at vision as it does at audition, and so on and so on and so on.
Yeah, the way I would put it is that to some extent, Steve already had a bunch of ideas about sort of neuromorphic networks that weren't bolted to anything, including cortex. Like if you look at the late 60s stuff and some of the stuff in the 70s, it wasn't really committed to any anatomical region, which is what makes it sometimes a little bit difficult to get into, because most people coming from a strong neuroscience background expect to hear the names of, you know, specific brain regions and much more specific circuits. It's eventually Steve started to do that, but it's still the main action is happening in the mathematical transformations. And if someone says, oh, the circuit is not like that, it's like this, it's not that difficult to kind of refactor some of these things to incorporate the subcortical stuff differently. So it may be that top down and bottom up is not, you don't just say that the top categorical node is a cortical area. Like you could, in principle, say that maybe an entire thalamocortical loop corresponding to association cortex is that node in some cases. I still think that the people are right to say that a lot of that is happening in cortex, though, because there's such a lot more like neural real estate there, that the loop, like there isn't like one thalamic cell for every cortical cell, and that must mean something. So yes, so here's what I was mentioning earlier about interstream competition. In the Artstream model, top-down excitatory harmonic sieve, which we already saw, is balanced by inhibition from the pitch summation layer to realize zero. As a result, feedback from the pitch stream layer to the spectral stream. So that's like the pitch stream is the categorical node, and the spectral stream is the feature set at that level, activates a matching process. So we've seen this before. That's how adaptive resonance theory works. And so you get this reinforcement so basically once a pitch is activated in a stream, it reinforces the corresponding frequencies that belong to that pitch. So there's some kind of filling in that can happen here. For some reason in these papers, they don't explicitly simulate the missing fundamental property, but I think maybe it's just very easy to get it to work with a model like this, I think. but also as far as I know, these models aren't learning models. Because I think that there's a reason for that. I think learning in these types of models is very hard to get to work. Like you can say in principle, it should work this way, but I think it's particularly hard to get it to work. So yes, so competition between streams for each frequency component presents a frequency from being simultaneously allocated to two streams. So yeah, so initially they kind of segregate completely. And then this key idea that will come up, and we'll kind of spend some time on it soon, is a conscious streaming percept is predicted to arise from a spectral pitch resonance. There's a specific example of a theme that Steve really hammers on, which is that all conscious states are resonant states.
It's not just that they are separate. These streams are very similar to the way in which he frames it for the visual part, where you can have multiple representations, and the combination of all of these surface representations is your percept, right? So in the same way, the set of all these so-called separate streams is the auditory percept. So what he did in the spatial domain, he is just sort of like pushing it into the temporal domain here as well. So it's not like they're going to be separate and they're not interacting or something. It's the sum set of all of them that is the percept.
Yeah, and what's nice about it is that even though there's a hierarchical element to it with category nodes and things like that, the conscious state is not merely the activation of the top down of the upper node. It's the whole resonant state. So it's a nice emergent kind of commitment, if you like. So these are some very nice looking simulations of, well, this is the input to the model, and these are the kind of split into two streams. So you see here, this is the one of them is the frequency map, and the other is the pitch map. I forget which is which, but I think this is probably the pitch map because it's more discretized looking. So you can see that the model basically produces exactly what you'd expect when you sort of draw out what the percept seems like, which you could think of as a critique. It's basically that there's a term for it, that isomorphism between conscious percepts and neural states, but not state in the trivial sense of some static state. A conscious state is isomorphic to some sort of spatiotemporal pattern, which some people quibble about it, but I find it hard to imagine that something like that is not true. We mentioned this before. They simulated this effect where the noise is actually required to produce that continuous percept. If there's an actual silence, you'll hear the silence. You can see this here, that in this case, there was some persistence of the category node up here, but it does eventually produce a silence. And here you see this sort of filling in. So the noise is sort of providing energy to kind of bridge the gap, basically. Very similar to what happened, similar things that we saw in the visual domain and in the motion percept domain. We can sort of gradually sink into this topic because it makes some statements here. Art suggests that stability implies intentionality. And implicit in the concept of intentionality is the idea that one can get ready to experience an expected event so that when it finally occurs, it can be reacted to more quickly and vigorously. And until it occurs, we are able to ignore other less desired events. So this is actually a kind of low-level technical consequence of the way the math of this all works. That when you have something that's been activated and it's falling off, you might not detect it. Then a subsequent signal can come on and bump it up. So you kind of priming can help things along. So things in the future can affect the past. But is this intentionality? I don't think this is what philosophers mean by the word intentionality. So it's a bit off target, I think. But if you replace that with basically goal-oriented and expectation-oriented perception, is important, but I don't think it's what philosophers call intentionality. Anyway, now we get to Sorob's law, which has some really awesome backwards effects in time related to language processing, but other kinds of processing too. So, or sound processing. So here, a phoneme deleted from a speech stream is perceptually restored when it's replaced by broadband noise, even when the disambiguating context occurs after the phoneme was presented. So here are some examples. It's hard to find good diagrams to kind of, but like, Saurabh, if you feel like just giving examples, please do.
I think the most convincing to me was delivery and deliberation.
Okay, that's the
no,
one,
that's
yeah.
that's actually here. Yeah, I was actually in the process of seeing if I can find audio clips of good phonemic restoration examples. So
Yeah, I found a couple on YouTube that were just sort of okay.
yeah, I'll look while
So basically, if you in delivery versus deliberation, you can replace the V/B with noise, and then when the rest of the word comes in, the percept, and you kind of have to take, if you don't have the percept yourself, you'll have to take our word for it. It sounds not like you're inferring that it must have been a B or must have been a V. You actually hear the B or the V. And this is where, you know, endless quibbling could happen about the difference between actually experiencing something and inferring it. But
or even reporting that you've experienced it, right? So it's one thing if I knew that I inferred it and said this is what I've interpreted the phoneme should have been, but it's completely different when you ask somebody after the fact, what did you hear? Right. And then they may actually just overwrite whatever the conscious experience in that moment was. Right?
Exactly.
And so there's this almost impossible thing that you have to do to disentangle what they've reported as consciously having perceived versus what they actually consciously had perceived, right? Yeah. But delivery and deliberation, I think, are great examples because acoustically, the initial portions are, there were initial arguments about phonemic restoration and is there enough information and maybe the way that you're co-articulating the phonemes that you could actually determine that based on the way you said delay, that it would be a V or a B or whatever. But actually, this is a great case where really the initial portions are going to be indistinguishable until that subsequent portion comes in, and that the subsequent portion actually literally will change what you've perceived in the earlier portion. So I'll look for potential examples here, but
find more. Yeah. So this is Saurabh's model, ARTWORD, conscious ARTWORD. There was an ARTWORD before that didn't model as many of these backwards effects. And I actually found it a little difficult to like make my own sort of summary. So I'm just going to paste some points about how the model works in order of how they are presented. So so there's two, and here if you see these numbers, these are the assigned cortical layers. So this is a laminar cortical model where there's an acoustical feature, an item region of cortex, and a cognitive working memory. So the cognitive is for sort of higher order objects that are combinations of sounds, sequences basically that are chunked together. So in the cARTWORD model, lower processing levels are responsible for early auditory processing, whereas higher levels process increasingly compressed and context-sensitive global representations, such as lexical entries, list chunks, and sequences. The pattern of activity across feature detectors within a prescribed time interval activates a compressed acoustic item representation or item chunk. As a sequence of item chunks become active, it is input to and stored by a cognitive working memory. As the spatial pattern of stored items in working memory unfolds in time, it activates a network called a masking field, about which more later. So these cells are called list chunks because each of them is a unitized or chunked context-sensitive representation of a particular temporal sequence or list of acoustical items. So it's not just one sort of low-level feature, but a combination of them. So there's conjunctive representation happening. And active list chunks, that's all the way up here at the top, do at least two things. They read out previously learned top-down expectations, going back down, that are matched against actively stored item chunks. So it's like, is the template that I was expecting actually coming in from the bottom up? And at the same time, they are open. They open processing gates. This is this one all the way down here, right? So it goes all the way from.
Yeah. Yeah.
So that's the processing gate, which enables top-down feedback from the working memory to interact with the acoustical features. So again, it's like a more complicated version of what we see in the simple art, which is that the upper category goes back down to the feature level.
I'll add one thing here. The terminology is a bit ambiguous, but not by accident, because if, for example, like one way to think of it is acoustic inputs coming in, maybe the post-cochlear sort of like, let's say, Fourier transform that you might expect at the basilar like membrane or whatever. Item chunks might be something like phonemes that get learned over that. And you could imagine list chunks at something at like a syllable level or something like that, let's say. Right. Now that's a pretty hard commitment to, where in those levels of organization, the sequences are getting learned and where they're being represented and so on. Whereas, phonemes, morphemes, syllables, words, there's no clear distinction necessarily at which level any one of these things is getting learned. And so we sort of left it ambiguous and vague because there didn't seem to be any reason to like make a theoretical commitment there.
So the working memory stuff, like we can both between the two of us, we can kind of explain it. But my feeling is that you have to kind of think about it a little while to get what's happening here, because even though the basic concept of spatializing a temporal sequence is not that hard to understand, I feel like if you're not used to thinking this way, it can take a little while. So I was trying to come up with like physical metaphors. It's like, how when you're carving a piece of wood, that like wood will curl up as the knife goes forward. So if you imagine the knife going forward is like the arrow of time, right? And this curling up is like stuff accumulating in space. That's kind of what's happening here, with multiple things happening, and then those sort of, so that all the processing is about what's happening presently, like at a particular moment in time. And this is where there's a kind of subtlety in dynamical systems. On the one hand, you can say that dynamical systems are good at incorporating the past. But in a kind of literal sense, a dynamical system that doesn't involve any explicit time delays is only interested in the present. So all effects of the past have to be explicitly manifest as things like working memory traces and the consequences of integration. It sounds like nitpicking or something, but it's interesting to keep in mind.
One other possible metaphor here. Imagine, for example, a pool of water or something, right? And I'm going to throw stones into this pool of water, right? And I throw a stone, it lands in a location in this, let's say, circular pool. It's going to cause some waves to, spread out from wherever that stone landed in the water. And then I throw another stone, and that stone lands somewhere else. And that stone now will have maybe higher activation. It'll result in higher or more sort of high amplitude waves than the previous one. Now we have two locations at which stones have occurred in this pool. And based on the level or amplitude of these waves, you'll be able to say when they occurred. And based on the location, you'll be able to say where they landed. Yes. Right? And so in effect, our working memory is somewhat like this, where we're taking this temporal sequence of things that are happening and saying not only what we think happened, but by representation, by virtue of representing the activation as a sort of marker of when they happened, all of that information is contained in the same spatial pattern.
So before we show, we'll have some simulation results so that we can sort of show what that looks like. That's a really good metaphor, because that's perfect for the spatializing of time. Because you could take a snapshot of that multiple ripple kind of pattern and infer things about the temporal sequence, with a lot of assumptions baked in, but that's basically what's happening here. So masking fields are embedded in here, and there's an interesting concept. So a masking field is a recurrent on-center Rossler network whose cells interact within and between multiple spatial scales. And again, here spatial is not exactly like space in the in Euclidean kind of sense, but with the cells within larger scales capable of selectively representing item sequences of greater length. So it's like different cells are attuned to different sequence sizes and are inhibiting cells that represent item sequences of lesser length. So there's like a hierarchy of inhibition going on here. And here's a diagram from an older paper on this, which I think captures it pretty well. So some cells have a certain span. They're interested in items of length 2, and they can inhibit only them each other, I guess. And then if it's things that are a little bit bigger, they're like items of length 5 different conjunctive items, conjoined items. And then the largest possible chunk that you can learn can inhibit all of them. And the reason all this is there is in the case of, say, language, if you're hearing like the word myself, ultimately you want to have the myself kind of node maximally active because that's the what you heard, but not hear my and self and elf. So even though those things came first and were complete in a sense, the self, which so this is a nice practical example of disambiguation. By the time you hear self, you're like, oh, all that stuff I heard before was building up to this. But before you hear the word self, things that are active for my and are also active. They're like candidates. They could win because if you don't say self, then my should win. So this is a way of kind of implementing this, which is that cells that are sitting waiting for a larger chunk will eventually win out. They're waiting for their summons, and for some reason,
Okay.
Yeah, go ahead.
I'll add one more thing. In addition to the conscious perception bit here, there's a very sort of relevant and important piece on learning where if you imagine you have a self-organizing neural network, and this is something that deep learning models today won't do, where if you have a category node that's activated at the very end, or in like a neural network deep learning sense, like the last layer where you have multi-class classification problem. In those cases, in that latter case, you'll know exactly, you'll have a representation for myself that gets activated when the input corresponds to the word myself. You'll have a representation for self, elf, my, all of the subchunks as well. And it already has to be pre-specified which thing is occurring in response to which inputs, right? Now,
Wait, what do you mean by that?
well, so if you imagine the task of these category nodes learning in response to inputs without feedback from an external supervisor or whatever, if the first word you learn is my, right? And I start saying myself, how do you know not to have myself be sort of an updated version of like the category node for my? Why should it not learn to start representing myself?
Yes,
right?
Yes.
Right. If all of a sudden I've learned to recognize apples in a vision model, in the absence of background clutter, let's say, and then all of a sudden, every time I see an apple, somewhere else there's, let's say, a cat, right? I should still represent these as two separate things, even though, and granted, this is not, I'm coming up with this as on the cuff. It's not a great, analog, but these are separate things. They should be treated as separate. And how does the brain self-organize to learn, sub and super sequence sort of categories like that, right?
There's a similar example. So do you remember when for some early one of these image recognition things, they found out that the template for dumbbell had an arm on it.
Mm-hmm. Yeah.
Because dumbbell in photographs typically occur with an arm.
Yeah.
So then they retrained without the arm.
And this is exactly relevant here, where it's like, if you've started to learn a category node for the word my, and it always then is preceded, let's say, after the fact by the word self. Why doesn't your category node update to represent the whole word? How does it learn to like treat these as separate things and so on? And so the learning piece is also very relevant here.
I imagine that the natural solution that many people think of, and this is anticipating the last bit I'll talk, is to stipulate certain time frames, which is that like only use the category that was stable every certain number of milliseconds. There's a kind of brute force way of like stating that early warning signs for some category don't get to learn anything.
And this is, to be fair, this isn't terribly different. It's saying that there's, you know, let's imagine there's maybe short-term memory of 3-4 chunks, items that can be chunked together. And then if you have a hierarchy of these things, what do they learn if you have that sort of masking field at multiple levels? But
right.
it imposes its own cap in a different way.
Yeah.
I joined late, so maybe this is a redundant comment, but isn't this basically a sort of combination of two of Steve's ideas? One is the shroud idea, and the second that in spectral timing, when multiple lengths of spectral timing can be associated, the longest one that can be associated always wins.
We haven't talked about spectral timing yet because he's actually put a separate chapter for that for some reason. That's not yet, that's coming up.
I agree on the first part. The second part, I would actually say it's almost the opposite in this case, where the shortest time span is the most representative. So let's say I've heard the word my, and I have learned words for myself, and whatever other supersets. Which words there should provide top-down feedback? The likeliest word to provide top-down feedback should be the word my. And it should be a better sort of candidate than the word myself, since fewer of its bottom-up inputs have been seen and observed, and effectively the masking field idea sort of builds that into the mechanics of how one might outcompete the other.
But for the brief period that my is active, it can learn something, right?
And it should, yeah, for sure.
Yeah.
But if you imagine so one of the things that we'll get to shortly is like top-down feedback is what enables things like filling in perceptually when, you know, parts of the speech are absent or malformed or whatever. And if I hear part of the word my, and I've activated my category nodes for my and myself, what's preventing, you know, me from hearing self, you know, top-down feedback from the category node for myself, as opposed to just the top-down feedback from the category node my, right? Because then you fall into an endless feedback loop.
Oh, right.
So the top-down feedback from myself would start activating the sa, the elf, and then all of a sudden that reinforces the activation of the category node for myself. And now every time you want to learn or hear the word my, you activate myself, provide so much top-down feedback that it activates the bottom-up inputs and, you know, runaway excitation and so on and so on.
Yeah. For some reason, the masking field, the way it works, and also the diagram made me think of like beasts that are sort of waiting to be summoned. Like there's a particular type of input it likes, and there's a bigger one and a bigger one. But anyway, so these are the simulations of, there's two of them here, but here's a simulation of a feature, an auditory feature with the gap, and then another feature. And so basically, if you go through this, you know how you read these, you kind of go from the bottom up. The inputs are the external, and then you have features. And the difficulty with reading one of these simulation plots is that when top-down excitation is happening, it's not the case that you can just look at the causality bottom to top. You know, it's what you see in the acoustic features is a consequence not only of its bottom-up inputs, but also the top-down inputs. That's part of what makes it a little challenging to kind of read it. But so the features come in, and you have different candidate possible chunks that match. then when this second one kind of comes in, eventually this chunk says, ah, that's the chunk that I recognize. And then eventually the topmost category shows up, and then you get at a kind of delay the categorized versions of the input. And here you see that if you insert noise, you get enough energy to populate that middle kind of term. Is there? Yeah. So one thing so I guess it's implied in what I just said, but could you elaborate a little bit on the resonance wave concept in this model?
Yeah. So the all conscious states are resonant states idea basically stems from sort of unfolding of super threshold activations across the feature representations and the higher level say list chunk or like grouped representations, and that resonant wave unfolds between if for example at the list chunk level or group representation level you have some, let's say, morpheme or word level representation, it'll activate the representations at the feature level, but it'll do so in a way that's sort of sequential, in a way that respects some of the way that they've come in terms of temporal bottom-up input, but also in terms of the top-down weights that have been learned as expectations. Like this sort of expects the sequence of bottom-up inputs, it's learned that, and so it'll excite them in a way that results in this unfolding wave of activation between the top-down node and the bottom-up inputs. The requirement for noise to result in a restored percept, and the sort of explanation that you get for phonemic restoration in the absence of noise, is that top-down input on its own, and this is true in all of Stieve's models effectively, top-down input on its own or feedback on its own without any bottom-up input is not sufficient to activate those bottom-up nodes or feature nodes. And so you need some activity in those bottom-up.
The 2x3 rule.
Yeah.
Is the 2x3 rule the same as the idea that top-down modulation is always multiplicative? Because they're not always multiplicative, right?
No, that's not the issue. The 2x3 is it's the conjunction of 2 out of 3 inputs to be present. That's not necessarily multiplicative.
Right. So basically, in a given sort of, often in a category node, you need bottom-up input and top-down input, or you could have a third thing, which is attentional modulation, right?
Yes.
Yeah. So that's the three. Any two out of those three are needed to excite a category node. So in this case, so the spatialization of a sequence is kind of happening here. So when you cut across at a particular point in time, you get a representation that captures this order in which things arrived. You can see that in the item chunks here, in the working memory here, and the list chunks. So the pattern recognizing mechanism, ART-like mechanism up here, doesn't have to do any buffering or keeping track of things. All it has to do is look at the current state, and based on the current state, assign a category. So that's what you get out of using this type of working memory representation. So that the working memory has to be structured like we talked about last time with this primacy gradient type of thing, where when you rank order the activities, that gives you the order in which the items arrived. So yeah.
One other thing I'd add is actually the top-down feedback can kick in from a couple different sort of mechanisms.
Mm-hmm.
One is, for example, like, as the bottom-up input's coming in, it activates a top-down category node or word or whatever that is the likeliest at that moment to be the thing that's, corresponds to the incoming input. But you could also
like whatever is currently here among the list chunks, right?
Yeah. And so like the words deli versus delivery, deliberation. As I hear delay, there's now, let's say in my mental lexicon, not many words that are going to complete that.
Right.
And so the top-down feedback might only exist for the words that could be possible, ways to finish that. At the same time, you could imagine semantic priming before you've even heard the bottom-up acoustic input or visual, you provide some visual feedback or whatever. Now you can actually influence through top-down feedback, potentially what people are going to perceive acoustically based on what they're getting either visually or through whatever other mechanisms. But that's it, that sort of semantic, let's say, or alternative like top-down feedback, it can exist as well, and it's different than the actual, like, this is just the likeliest completion of the acoustic input.
Right. And what I like about that is that, like, when people complete each other's sentences or predict what they're going to say, it's amazing how well or successful that can be with close friends. And sometimes they haven't even said anything yet, and you know what they're going to say or what they're going to bring up.
It's certainly a wild trip.
Yeah. So this is a nice seg into this wider topic of like the conscious percepts and time. So this is from your paper. So the current theory proposes that silence will be heard between words whenever there is a temporal break between the resonances that represent the individual words. So like if this green bit wasn't here, meaning that there's a kind of a percept node that has been activated, you would experience silence. And presumably on either side of where there's nothing that has been activated in this particular set of categorical nodes, that means silence. So the thought that comes to my mind, which is that, so like what's going on over there, which, silence, I guess. And then you can ask, is something always resonating in some modality or in an amodal space? Now when I'm zooming out to mean the whole brain, not just like the auditory system or whatever, because now you can start to make sort of very speculative but askable questions about when resonance happens or how often and things like that.
You can actually make the case that you're always resonating, whether you're conscious. This is the Steve game, right? Like it's the best game that he plays, which is that you can always keep having resonant states, but they need not be conscious states, right? So you can completely avoid such a question in a way.
Yeah, unfortunately, or fortunately, whatever. But then the fun question, again, askable, but I don't think answerable, is can there be amodal silences, right? Meaning that nowhere among the types of resonances that could produce a conscious experience are there any resonances. And is that just sleep or anesthesia? So you like anesthesia is, in my opinion, the most practical version of the question of consciousness, and you can start to maybe ask these kinds of questions. I mean, if we knew of like neural correlates of a resonance, if there was a hallmark of it, then anesthesiologists would be interested. But I don't know whether we're anywhere near there yet.
What about meditation?
What about meditation? Exactly. In fact, I asked on Twitter today about it. Does anybody have recommendations for papers on this question of when are we conscious and about all this backward effects in time? And somebody brought up meditation and the idea that you can have a conscious experience that doesn't have an object. I've heard this a lot.
I think I've had those experiences.
Oh, wow. Okay. Because like, I don't know whether I've had that experience, at least not meditating, definitely. But I don't want to doubt that people have had that sort of non-dual experience, right? And so thinking about that in these terms, is it a lack of resonance, which kind of leans towards a Buddhist way of thinking, or is it a kind of macroscopic resonance, which leans towards a kind of Advaita, all is one kind of way of thinking? You can go either way with it. But so asking on Twitter actually led me to this paper, which is from 2020, and very relevant to stuff that was in Sorob's model, but unfortunately they didn't look at Sorob's model. So it's about long-lasting post-dictive effects, revealing. The title is not very good because it's not exactly what the paper is about, but yeah, they basically look at these post-dictive effects. So the backwards effects in time are examples of that, where something later seems to change what happens earlier. But when you, as long as you're looking at the model, it doesn't seem like there's anything particularly paradoxical happening. But then you ask, well, what was I experiencing before the disambiguating input came in? Unanswerable sort of question, but very askable. So anyway, they go through, it's a short paper, but they review some interesting data on pretty late post-dictive effects, up to like 400 milliseconds. So there's a lot of interesting psychophysics. All of it I think is kind of modelable in the Grossberg scheme. And I think this Herzog in one of his earlier papers, I mean, he has looked at Grossberg's papers. So yeah, there's this age-old kind of puzzle. Is consciousness a continuous stream, or is it in some sense discrete? Part of me wonders whether this is even a meaningful question. But you know, here's a diagram of how they think about it. So there's this, what many people seem to think, including, you know, a lot of scientists and philosophers, is there's some kind of continuous cinematic way of talking about experience, which is that there's like movie frames, and you know, either there are infinitely many of them or there are finitely many, but there's no gaps among them, and your experience is like continuous, like a movie is. I don't know, it seems like it's a bit circular. And then there's this discrete cinematic idea, which is more like an actual movie reel, where there's, you know, something is happening between frames, but that something does not enter into conscious experience. And then there's a sliding window, which starts to be kind of like these first two, I think, are prevalent and have been around for a very long time. Certain Buddhist writings seem to talk about moments as if those are the only things that are real, and they're like fleeting, fragmentary. So existence is just a fragmentary chain of moments. And even when Hume talks about causality, you get the impression that he thinks that the universe consists of moments. And in fact, the ontological question of nature of space-time and the subjective question of the nature of consciousness, they kind of merge in this particular topic. This continuous retention thing, I think, is much easier to get to start to approach if you really think about language and psychophysics experiments, like language, music, things like that. But even this, ancient people were aware that, you know, past leaves traces in your memory, and that you're using that. But whether it was, I mean, the concept of a sliding window kind of requires a certain amount of calculus, I think. And then there's kind of what they're going for is this buffer idea of some sort. And these, I don't know what they mean by sort of the duration inside the window. And one, I don't know how it shows up for you on your screen, but this color 5 phenomenon is one of my favorite examples of a backwards effect. And they show the red, so it's just 2 dots, there's nothing moving, there's no interpolation. And this, for the slow, for the longest time difference, you see a red followed by a blue. And then when it's faster, you start to see something going. And they space out the different things. So it's not the case that you're seeing a rhythm of multiple, you know, presentations at a particular time gap. It really is the case that after you've seen the blue, it's as if you were seeing movement. It's really quite striking. If you don't see it on this screen, if you look for 5 phenomenon and go to Google image search or something, you'll find it. It's on Wikipedia, I think. So post-dictive effects, or when a late stimulus can affect perception of a previous stimulus, and they review like a bunch of pretty long effects. And this one, just somewhat complicated psychophysics experiment, but it's quite interesting. And here's one of the experiments that shows that integration of visual information can be going on for up to 450 milliseconds. So they presented these lines composing of 2 segments, one on the left and one on the right, that in subsequent frames are moving further and further away. So that you get this impression of, you know, moving sideways like that. And somewhere in this chain of frames, one or more of those segments is split. There's like a vernier split, so they're no longer aligned, and you can perceive that this misalignment has happened, but you won't be able to say when. And if you have an alignment in one way and then another one, it kind of integrates. And if you have an alignment and the opposite alignment, it kind of compensates for that misalignment and you no longer see. But after 490 milliseconds, you'll see a fresh misalignment. So that's quite striking. So it's not simply that you're doing a running average, but there seems to be a windowing effect, because like after a certain amount of time, you seem to be starting afresh. So that's one of the line of evidence for a frame. But this is way longer than any frame that anybody's talked about before, because we already know that there are situations where 100 milliseconds is where the integration happens. And we know that you can, for instance, hear a gap in sound of a couple of milliseconds. So depending on the modality and the experiment, these things are really, really finicky and dependent on the specific experiment. You can get different windows. So what does that mean for any global notion of when am I conscious, or how am I integrating the recent past to produce, for like as in Saurabh's model, category nodes of conscious features. So they talk about the sliding window problem, but I think that
for people interested in this kind of like sliding window / frame, Susanna Martinez-Condi and Steve Macknick have done a lot of work. I think this whole meta-contrast thing, sequential meta-contrast thing, is partially started by them. They've actually, I can send a couple of papers maybe in the Zoom chat. They've actually talked most about like the presentation of two stimulus one after the other, and let's say that I put in a mask or silence or whatever between them, then you won't even be aware that the second stimulus was presented, all that stuff. So they use that as a basis for what you can call as a perceptual window framing. So it's like that's their motivation for saying that we don't really perceive in a continuous manner. We're kind of like integrating something over a given time period, and then that's
it's very strange the way that this window works, because one thing you might think is that the oscillations create windows. Some picking oscillation, very often it's alpha.
That's
the weird thing.
It is very much alpha. So that's one of the first papers that they did in, if I remember, way back in early 2000s, they did this paper. There's been some time since I looked at it. I was working with Arash.
Yes, but what I'm saying is that even in those experiments, sometimes the alpha gets reset by a stimulus.
Okay, here is another thing. Almost all low frequency signals will be reset by multiple things.
This is the thing. So you can't have your cake and eat it too when it comes to these frames. Either you have a sort of train, right, or like some kind of forced set of windows, and it's like whatever you do, it has to be in one of these windows to be integrated. But you also have, like Karthi just said, like resets happening. And then the windowing effect will proceed from that reset. So it's a tricky thing to think about.
The reason why I'm talking about Macknick and Susanna Martinez-Condi is they've actually kind of gone a little further, which might be more interesting for a larger number of people. They've actually tied all this to how people's attention and awareness works when a magic trick is being played.
Whoa.
They are one of the very few, for people who don't know, Martinez-Condi is the one who actually hosts the Visual Illusions of the Year website. But they actually have written a book where they pretty much sat with a bunch of magicians, asked them how they do it, and then kind of inferred, like how magicians, pull the sleight of hand trick. And you realize that most of it, apart from like, forcing your attention elsewhere, is this, they're actually working on certain time periods. If it takes anything longer, it actually fails for them. So they've actually compiled all of this in their work. So that's the other thing that I would like to point out about, like, if people are interested in this problem, also read Macknick and Susanna Martinez-Condi's work on magicians and how magic tricks work.
But so the sliding window problem,
I would agree that's a really interesting literature. But I just had a general comment to make, is that don't you get adaptable windowing for free via peak shift?
Peak shift in what?
So you remember the first exercise that Ennio had you do?
Right. But like, so you mean like visual peak shift?
Yeah, but temporal peak shift.
Oh, but like what, in what phenomenon?
In any of these phenomena, that you can separate the windows when the underlying evidence and your smoothing function creates a peak shift.
Yeah, I like that. In fact, that was my response when I saw this sliding window problem, is that Sorob's model or extensions of it, or anything that involves forming an arc-like representation at the end of some period of integration. There's no fixed time at which any of this happens, but there is a type of discreteness, but it's not the discreteness in time. It's the fact that there are thresholds. So, so either a fixed threshold in the case of like rectification, or an adaptive threshold in the case of pure competition. Meaning that when something becomes a winner and becomes adequate to produce resonance may depend on the presence of distractors and things like that in a pure competitive system. So I was thinking that, so here there's a sliding window thing, but Steve has modeled this sort of motion effect. And I don't think he had too many percepts problems. So basically they're saying that if I'm using a sliding window and integrating, then initially, before I see the second stimulus, I'm perceiving a stationary stimulus, then nothing at all. And then when I have, or then when I include both, then I get the motion. So, and then all those times in between, the window has to produce something, and it's producing stuff other than what you experience. But that's like kind of bolting the window to that anything that gets processed in that window has to be experienced. Whereas in Steve's case, he's only making a positive claim. When something is resonating, it's in consciousness. When nothing is resonating, Steve has nothing to say about it, right? Am I right about that? So that's how I see that this particular problem. I don't think it matters if you're using a competitive system. But the broader issue is this famous question of whether consciousness is continuous. So yeah, so it's like we feel that things are happening continuously. Or, this can actually go wrong in some states. And despite this appeal, there's all kinds of psychophysics to say that it won't work. So their model at the end of it is this two-stage model. So basically saying that the unconscious is more or less continuous, processing with high spatiotemporal precision, because we know that we have really, really high spatiotemporal precision, which sometimes becomes conscious, as is the case with a 3 millisecond gap in a sound. So there are these, so that somehow, so there's a window of unconscious processing, which I'm not very convinced about. And information from this buffer is collapsed. And there again, this sort of, I don't know whether a buffer is the right way to think about it, but it may be related to this working memory thing. But in Steve's working memory, I don't think buffer is the right term for what's happening. Because typically when you think about buffers, you think about them being cleared or things being moved out of there to be processed. So I don't know whether buffer is right. But this is fun. A counterintuitive implication of our two-stage model is that it is in opposition with the feeling of a continuous stream of perception, which arguably stands at odds with qualia realism. We propose that with each conscious percept, an internal model is updated, which gives rise to the experience of the flow of time. That last bit that I just read sounds like Steve models, that the update, whether it's fixed to a window or periodic or whatever, that you know, whichever thing is in resonating gives rise to the experience of time. But then this last line I can't make any sense of. In some way, the high spatiotemporal resolution of the unconscious processing periods may give rise to the illusion that consciousness itself is also continuous. Do not know what that means. But yeah, that's all I had. Questions, comments? I can stop the recording if no one wants to ask questions on the video. Okay, folks.
Are people familiar with this, with Emilio Salinas and Terry Stanford's work on really detailed saccade timing?
No.
I dropped one of the
Yeah,
references
I'm
in
looking at it now.
chat. I think they present pretty convincing evidence that there's no perceptual windowing.
In this particular task.
Well, in the generation of saccades.
Ah, okay. Yeah, it's really weird because like
And
you
you're still
want like
recording, by the way.
more than
Actually,
even the
it's the other way
continuity
around.
thing.
It's the other way around. It's the saccades that are creating the perceptual windows, if at all.
Yeah. So that I like. I like that.
And once you do that, you don't have to restrict it to any cycle. You can assume the saccade or whatever is whatever quasi-rhythmic, quasi-whatever. And whenever it happens, it is going to create, and you see it reflected every time, right? Like anyone who has done either EEG or any LFP level recording, every time you look at the evoked response, all the low frequency evoked response dip when you have a saccade or a stimulus presented. So that's a reset thing that Yohan was talking about. All of them reset the moment, say, a saccade happens or a stimulus is presented or a motion happens, unless it's smooth tracking of a sort. Anything that is like an event will actually be enough to trigger a frame, but not the other way around. A frame will not trigger the event of a saccade or something like that.
What, really? Why not?
I don't think so. I've not seen it in my data, so I'm going to be very partial.
But wait, you can voluntarily saccade, right?
You can voluntarily saccade, and once you saccade, you can do a lot of things during the time period before you saccade back to something else. So it's sort of like during saccade, you don't see anything. So that might be whatever the unconscious buffer or whatever they want to call it. I don't have any views on that.
Yohan, you said you were going to turn off recording?
Oh, it was not off?
Ooh, I said so many things.
You can trim it afterwards.